All right, guys, we just finished our little demonstration with the static ball and did a few things with the electric charge. We had some pretty good explanations as to what was happening. We'll talk a little bit more about those explanations and kind of say what was good about those explanations, what was bad about those explanations as we go on with the notes here today. Fundamentally, though, in order to understand what we just saw with our demonstrations, we've got to define a few things. First of all, we're going to define positive charge and negative charge. Can anybody tell me where positive charge comes from and where negative charge comes from? What are the things? What are those little things that cause positive charge? Or what are those little things that cause negative charge? Okay, you're on the right track. You're not quite right, but you're on the right track. The answer there was a positive charge wouldn't have any electrons on it. It would have what then? Okay, protons are the opposite of electrons, right? Positive charge doesn't come from having no electrons. A positive charge doesn't come from having just protons. A positive charge comes from... Good. A positive charge comes from having more protons than electrons. So if you've got 1,000,000 electrons, that's okay. You can still have a positively charged object as long as you have at least 1,000,001 protons. That make sense? You can all answer this next question for me then. Where does negative charge come from? If positive charge comes from having more protons than electrons, then negative charge comes from having... Yes, you're all thinking it. Nobody's just saying it. It comes from having more electrons than protons. The one thing I haven't put up here is the neutral object. Neutral object comes from having same number of protons as electrons. An atom is neutral, right? An atom is neutral. Hydrogen atom has 1 proton. How many electrons does a hydrogen atom have? 1 electron, right? Carbon atom has 6 protons. How many electrons does a carbon atom have? 6 electrons, right? Carbon atom versus a carbon ion. Lithium atom versus a lithium ion. Hydrogen atom versus a hydrogen ion. What's the difference between an atom and an ion? Chemistry people know this, right? An atom is neutral, an ion is? It has charge, right? An ion has a charge. Where does it get the charge from? It has either an extra 1 or 2 or 3 extra electrons or 1 or 2 or 3 fewer electrons. So it becomes charged from having either an excess of electrons, extra electrons, or having fewer electrons. It's neutral when we have an equal number of protons and electrons, and it's positive or negative when we have an extra amount of protons or a deficiency of electrons. This is a picture of the atom right here. If we're talking about protons and electrons, it's probably a good idea to know where these protons and electrons are, what exactly they are. This is the nucleus of the atom in the middle here. Tell me what's present, protons, neutrons, or electrons in the nucleus of the atom. Don't make the mistake that I made in my 3rd year modern physics course on one of my exams, where I said the electrons make up the nucleus. The electrons don't make up the nucleus. What makes up the nucleus? Protons and neutrons. Protons, of course, are positive, and neutrons are neutral, right? There's no charge for neutrons. So neutrons we're not going to talk about a lot in this unit because they don't result in charge whatsoever. Protons we won't talk about a ton, even though they do result in charge. You're going to see why we don't talk about protons a whole lot a little bit later. What are these things that are orbiting around the nucleus here? These are the electrons, right? And the electrons have a charge that is what? Electrons are negative, right? So again, if you got 2 protons and you get 2 electrons, it's neutral. If you have 2 protons and 3 electrons, then it's negatively charged. 2 protons and 1 electron, then it's going to be positively charged. We're talking about this on the atomic level, but it also works for objects, right? You rub a balloon against your hair, that balloon sticks against the wall or the ceiling, right? Well, it sticks against the wall or the ceiling because it's got a charge. If it's positively charged, it's got more protons than it has electrons. If that balloon is negatively charged, it's got more electrons than protons. The unit of charge, the unit, not the symbol for charge. The symbol for charge, by the way, is Q. It's a lowercase q. The unit for charge is the coulomb. The symbol for speed is V. The unit is meters per second. The symbol for energy is E. The unit is joules. The symbol for momentum is P. The units are kilograms meters per second. The symbol for charge is Q. The unit is coulombs. That's named after a guy, Charles Augustin de Coulomb, that did some work with electric charge. Now, we all have a kind of an intuitive grasp as to what a kilometer per hour is. You know, what that value means, what a joule is, what a kilogram meters per second is, and so on and so on and so on. But we don't a coulomb, because it's the first time probably that we've ever heard that unit. What is a coulomb? How big is a coulomb? It's big. Really big. In fact, it's so big that it would take 6.25 times 10 to the 18 electrons to make up 1 coulomb. That's 625 with 16 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's how many electrons you need to have to make 1 coulomb of charge. That's our basic unit of charge, but it's a big unit. So what you're often going to see for charge is a microcoulomb or a nanocoulomb, some prefix in front of it. Because it's not common to have a whole coulomb of charge. That's a lot of electrons. It's more common to have a microcoulomb or a nanocoulomb of charge. Micro, by the way, is 10 to the minus 6. Nano is 10 to the minus 9, but we don't have to remember that because that's on our data sheet. We've talked about the electron, the proton. We've talked about the unit for charge, the coulomb. We've talked about the fact that it needs 6.25 times 10 to the 18 electrons to make up a coulomb of charge. Where do we get the charge of an electron? Because that's something we're going to use pretty often this year. The charge of an electron, by the way, is 1.60, negative I should say, negative 1.6 times 10 to the minus 19 coulombs. The proton is positive 1.60 times 10 to the minus 19 coulombs. Same charge, opposite sign. Those are numbers that we're going to use so often that we may very well remember the values of those charges. And if we do, that's great. But if you don't, that's okay too, because we can always look on our data sheet to find the values of those charges. And I'll show you how to find it on your data sheet in just a second when you're done copying this. If you open your data sheet to the page that says Physics Data Sheet, and you look on the right-hand side, you're going to see all these different particles. Most of these particles, you don't really know what they are right now. We have talked briefly about the proton, neutron, and electron. The alpha particle, we'll use data for that later on this year. Okay, the positron, the electron neutrino, and so on and so on and so on. We're going to know what all that stuff means later on this year. What I want to focus on right now are these two things, the electron and the proton. It says the charge of both of those are 1e, negative 1e and positive 1e. What does that mean? What's an E? An E stands for elementary charge. If we go over here to the left-hand side, we see that the elementary charge is 1.60 times 10 to the minus 19 coulombs. So, what's the charge of an electron? We already said that, right? We put it in the last page of notes. But if we have to look on our data sheet to find the charge of an electron, we would find that it's negative 1 times the elementary charge, 1.6 times 10 to the minus 19. The proton is positive 1 times the elementary charge. Now, even though right now you have no idea what an alpha particle is, nor will I tell you right now what an alpha particle is, you could find the charge of it pretty easily, right? It's 2 times the elementary charge. So the charge of an alpha particle would be 3.2 times 10 to the minus 19. Okay, right now, I want you to be able to find the charge of the electron and the proton. And because it's put on here in a slightly different way than we're used to seeing, right? Q is equal to 1.6 times 10 to the minus 19. It's kind of told to us in a bit of a roundabout way on this data sheet. I want you to be familiar with how to find it. Okay, we good with that? All right, a couple more terms here. First term I want to define here on this page is a conductor. There's a couple kinds of conductors that we can think of, right? A heat conductor, a thermal conductor, and an electrical conductor. Obviously, we're talking about electrical conductors here. We want to take a stab at what an electrical conductor is. We all know what an example of an electrical conductor is, right? Piece of metal is usually a pretty good conductor. What's the difference between a conductor and an insulator in the context of electricity? Colin? Yeah, okay. Colin said a conductor can continue current or carry current. Sure, an insulator doesn't. Okay, good, good. Fundamentally, why is that the case? You're absolutely right, Colin. There's nothing wrong with what you said at all. But more fundamentally, we say a conductor is a material in which electrons in the outermost regions are free to move. So why does it carry a current? Because the electrons that are in those atoms of that material can leave. The electrons can go somewhere. Whereas an insulator keeps its electrons. Electricity is moving electrons. If you want electrons to move from one place to the other, to be conducted from one place to the other, you need a material that has electrons that aren't tightly bound to the nucleus. A material in which electrons are free to move about versus a material in which the electrons are tightly bound to the nucleus and aren't so free to move about. Now, there are varying degrees. You don't need to copy this page down, by the way. There are varying degrees of conductivity. We're not suggesting here when we define a conductor and an insulator that something is either a conductor and it equally conducts equally as well to every other conductor, or something is an insulator and it equally insulates as every other insulator. There's varying degrees of conductivity. These things up here are good conductors. The relative magnitude of the conductivity basically just says this is how much better of a conductor it is than something else. So if we say, let's say iron has a conductivity of 10 to the 7, and silver and copper are 10 to the 8, then silver and copper are about 10 times better of a conductor than, say, iron would be. You can see that you got mercury, copper, aluminum, iron, carbon. What do you see in common about almost all of those conductors? What do they have in common? They're metals, right? They're almost all metals. Metals tend to be good conductors because metals don't hold on to their electrons quite as well as other things. Take a look down here now. These are insulators. They still conduct. Right? Insulators will still conduct to some degree, but you can see the relative magnitude of their conductivity is significantly lower. Look at rubber. It's 10 to the minus 12. Okay, that means that iron, which is 10 to the positive 7, is about 10 to the 19 times better of a conductor than glass is. So they still conduct, but because they have a relative magnitude of conductivity that's so low, they conduct so much worse than these things that we see up here. What do you notice about these? Well, they don't so much have things in common other than what they're not. They're not metals. You don't see metals down here in the insulator category because metals lose their electrons easily. These things in the middle, 10 to the minus 9 to 10 to the 3, they're kind of like conductors. They're kind of like insulators. We call them semiconductors. You've heard that before, right? You've heard that term before, a semiconductor. Okay. You don't need to remember any of these numbers, nor do you need to remember even the materials, other than metals tend to be good conductors, and things like glass and wood and rubber tend to be not so good conductors, or good insulators. Almost done here today. We got 3 laws of electric charge to talk about, and then we've got one more law that's kind of related to this to talk about, and then we're pretty much done for the day. The 3 fundamental laws of electric charge that you have heard before, you just may not remember them. First one, doesn't matter what order we do them in really. Opposite charges attract each other. We talked about that with our demonstration, right? Opposite charges attract each other. Second one, take a stab at what the second one is. You can tell me now that you've seen the first one. If opposite charges attract each other, then good. Same charges repel, or like charges repel. By the way, when we say opposite, we mean positive and negative. We say like charges, we mean either positive and positive, or negative and negative. When we say attract each other, we mean come together. Repel each other means push each other away. Third one's a little bit trickier. Charged objects, so objects that are either positive or negative, attract neutral objects. We're not saying that a proton attracts a neutron, because it actually doesn't. A proton doesn't attract a neutron electrically. It does using another force, but not an electric force. Protons, neutrons is not what we're talking about here. Electrons, neutrons is not what we're talking about here. We're talking about charged objects. So you got a balloon that's charged. Attracts neutral objects. You've got a wall that's neutral. They're going to attract each other because charged objects attract neutral objects. Now, let's go back to the demonstration that we did with the pop can against a static ball and the bubbles against a static ball. Those bubbles in that pop can were initially attracted to the static ball. The static ball, I'll tell you, has a negative charge, a massive amount of negative charge. Electrons get carried through that belt up to the top. They get deposited on the dome. The more electrons you have, the bigger the potential difference is, the bigger the voltage is. You get a massive amount of electrons built up there. This pop can is probably going to have what charge right now? Neutral. Those bubbles are probably going to have more or less what charge as they come out of that container? Neutral. So what was happening to that pop can and that bubble as they were approaching the top of this static ball that has a massive negative charge? There's our neutral bubble. What happens to it? It's going to get attracted, right? Neutral objects attract charged objects, or charged objects attract neutral objects. So this neutral object was being pulled toward this charged object. Now, this charged object was also being pulled towards that neutral object, right? By an equal and opposite force. That's Newton's third law. But we know that that charged object wasn't actually moving toward the neutral object because, why? It's a lot heavier, right? It's a lot heavier. It requires a much bigger force to actually pull it towards it. There was a force of attraction there, though, but it was the bubble in the pop can that you saw being attracted, you saw moving towards the top of the static ball there. So neutral objects were attracted to charged objects. Then what happened? All of a sudden, at one point, this neutral object started being pushed away now. Neutral objects can't be pushed away from charged objects. That would violate the third law of electric charge. So what was happening? It's going to get more electrons. Yeah, it's going to get more electrons. Right now, it has, I'm drawing it as 2 protons and 2 neutrons. But the reality is, of course, it's got many, many more than 2 and 2. Bottom line is it's an equal number, though, to make it neutral, right? When it gets close enough, electrons can discharge. Electrons can go from this static ball over here. So now it's got a whole bunch more electrons. What's the charge on that bubble or that pop can now? It's negative, right? So what happens now if you get a negative object and a negative object? It's no longer going to be attracted. It's going to be... Okay, Good question. Good question. We'll come back to that one in just a second, Matt. Very good question. Okay, let's say this is the pop can right now, okay? This pop can has what charge now? It's negative, right? So if it's negative and this is negative, it's going to be pushed away. It's going to be repelled away. Now, Matt asked a great question. He said, if it only discharged into one bubble, why are they all being pushed away? Okay, that's a great question. What happened in the case with the bubbles, they're all lighter. It doesn't take nearly as much force to push them away as it does a pop can, right? You get a whole bunch of bubbles coming in here. They're all neutral. They're all being attracted to the static ball. Then one of the bubbles hits the static ball. When it hits the static ball, you get a bunch of electrons being transferred to that bubble. What happens to that bubble when it gets a whole bunch of extra electrons? A whole bunch of extra electrons repelling each other. It pops, it breaks. Well, now this electron that has a whole bunch of, this bubble that has a whole bunch of extra electrons breaks and splatters. What happens to the pieces? They go everywhere, right? Including those bubbles. Now these bubbles that were neutral have gained electrons from this splattered bubble, and now they're all negative, right? So then now they're all going to be pushed away from that. Now, they're not negative by a ton, right? They're not like really, really highly negative, but because they're so light, they don't need to be highly negative. They don't need a very big force to push them away. Does that make sense, man? Great question. Similarly, I don't know if you guys noticed that when we did the demonstration, not only were they pushed away from the dome, they were actually pushed away from each other as well. They were pushed away from each other after the first one hit because, again, they're all negatively charged. They're not only going to be pushed away from the dome, negatively charged dome, they're going to be pushed away from negatively charged other bubbles too. Okay? One more law that we're going to talk about, and then that's it for the day. This one doesn't fit within the laws of electric charge, but it's still related to it. We call it the law of conservation of charge. It's like the law of conservation of anything else. The law of conservation of momentum. Momentum can't be created or destroyed. We don't usually phrase it that way, but that's ultimately what it means. The law of conservation of energy. Energy can't be created or destroyed. Chemistry. The law of conservation of mass. Mass can't be created or destroyed. The law of conservation of charge. Charge can't be created or destroyed. You can move it around. And we saw just a minute ago, right, when the bubble hit the static ball, charge moved. When the pop can came close to the static ball, charge moved. Charge moves. You just can't create it, and you can't destroy it. By the way, if charge is going to move, if charge is going to be transferred from one to the other, what kind of charge do you think it's going to be that's going to move? Positive or negative? Why? Yeah. What's in the nucleus? The protons and the neutrons, right? What's surrounding the nucleus? The electrons orbiting around. The electrons are attracted to the nucleus. They don't want to go anywhere. But they're not nearly as attracted to the nucleus as the protons are. They're held in place by what's called a nuclear force. It's a strong force, and it doesn't want to break up. It can break up, but not under normal electrical circumstances. And you get a nuclear reaction if it breaks apart. Okay, most times, the protons are going to stay in the nucleus. They're certainly much more tightly bound to the nucleus than the electrons are. So if you get a little bit of energy, due to friction or whatever, pumped into this atom, what's going to leave as a result of that little bit of energy? It's going to be the electrons, right? So when we're talking about electricity, if something moves, if charge is transferred from one thing to the other, it's going to be the electrons that move. Only because the protons are too tightly bound inside that nucleus by the nuclear force. All right? So charge can't be created or destroyed. It can be transferred from one place to the other. There's a whole lot of implications of that. Only one implication that I want to really talk about today. And that goes to this example, this mathematical example. It says, Not sure why this is underlined and italicized here, but it says a ball that we're conveniently calling ball number 1 with a charge of 3 coulombs touches another ball that we're calling ball number 2 with a charge of -1 coulomb. The first ball then touches the third ball with a charge of -5 coulombs. What's the charge on all 3 of these balls? How does this relate to the law of conservation of charge? We'll see in a second. How are we going to go about solving this now? Well, we know that the total charge has to remain the same. So let's figure out what the total charge is here, okay? We got it plus 3 coulombs, -1 coulombs, and -5 coulombs. Okay, charge of 1, charge of 2, charge of 3, and then the total. We start off with a charge of 3 coulombs, -1 coulomb, and -5 coulombs. What's the total charge there? 3 plus -1 plus -5 is -3 coulombs. These objects are going to touch each other. They're going to redistribute charge, move charge from one place to the other, but we're not going to create or destroy. So the total charge is always going to remain here, -3 coulombs between these 3 objects. When object 1 touches object number 2, the goal, Shane, is to balance the charge. Now, it depends upon the size of the object. It depends upon the shape of the object. Sometimes the charge won't balance. But whenever we do a question like this, we'll assume that the objects are more or less equally sized, more or less equally shaped, so that they can both hold the same amount of charge. In other words, when we touch them together, they'll balance. They always try to balance. But if you get an object that's really, really pointy and then another object that's really, really round, the pointy object can't hold as much charge as the round object, so they can't balance. We're going to assume that they do balance every time we see a question like this. What are they going to balance out to be? -3 touches -1. They're going to balance out to be +1 and +1. Anybody see where that comes from? What do we do, Jade? Yeah. Yeah, exactly. It was actually the other way around. You had 2 coulombs of charge going from the second object to the other one. So that one made this one less negative because it lost -2 coulombs of charge. This made this one more negative or less positive because it gained -2 coulombs of charge. Basically what we did is just average them out, right? We add them up, divide by 2. That's the effect of it. Charge moved from 2 to 1, but the effect is that we add them up, divide by 2. Now, what's charge 3? It stays as -5 coulombs, right? We haven't done anything with that yet. Let's add these up just to make sure that we got the total charge of -3. +1 plus 1 -5 is -3 coulombs, so we're still good. Then what happens? Then the first ball touches the third ball. So now we've got the first ball and the third ball, +1 and -5. What are they going to balance out to be? The one that's -5 transfers electrons to the one that's +1. But how much? Well, average them up. +1 plus -5 is -4. Divided by 2 is -2. What's charge number 2 going to be here? What's it going to be? Somebody said it? +1. Nothing's happened to it, right? In the first event here, we touched 1 and 2 together. They balanced out to be +1 and +2, +1 and +1. The second event, we touched 1 and 3 together. They balanced out to be -2 and -2. Let's add these up to make sure we get -3 again. -2 plus 1 plus -2 is -3. So the final charges on all 3 of these objects are -2 coulombs, +1 coulombs, and -2 coulombs. Over this unit, we're going to see quite a few implications of the law of conservation of charge. Okay, this is probably the simplest, most basic implication that we'll see. Good news. That's it for today.